Hello everyone, welcome to this session about nonparametric tilted additive model. Let's start with a brief introduction about regression estimation. We use regression analysis in most of clinical trials or observational studies for finding and describing the association among the predictors and the outcome of interest. In recent years, nonparametric regression models are more popular because first, they provide consistent estimation of a regression model. Second, they are robust to model misspecification. Third, they are really good for detecting nonlinear associations. And the last one, they are data-driven approaches. Okay, here in regression estimation, with all settings that we know about the regression model, the aim is to estimate the R, the unknown unknown regression function. Here, we only have one predictor in the model, and we want to use the nonparametric approach to estimate this unknown function. From different estimators, we will focus on kernel-based regression estimators. This type of estimators rely on kernel and bandwidth. A kernel is a weighting function that assigns weights to observation in distance to target point. And this distance is bandwidth. There are different types of kernel-based regression estimators. For example, we have Nadarya-Watson estimator. But this estimator suffers from two biases, design bias and boundary bias. So the local polynomial regression estimators have been introduced to address these biases. And they somehow overcome the limitation that the Nadarya-Watson estimator has. However, the asymptotic bias of this estimator relies on a smoothness of unknown regression function, design density, and also choice of kernel, and the polynomial degree of local fit. To overcome to this limitation, we have infinite order flat top kernel estimators. In this estimator, the asymptotic bias only related to a smoothness of unknown regression function. However, it comes at the cost of selecting a special type of kernel. The kernel should be infinitely differentiable. To take advantage of both infinite order flat top kernel estimator and local polynomial estimator, we propose applying a tilting technique, which develops an estimator that has the same convergence rate as the infinite order flat top kernel regression estimator, regardless what type of kernel we use. Okay, what is the tilting technique? A tilting technique applied to an empirical distribution leads to replacing 1 over n as a data point weight by pi. It seems that we are using actually a general multinomial distribution for weighting the data points. So in this approach, we need to estimate PIs or tilting parameters. There are two different approaches to do that. First is empirical likelihood method, and second one is distance measure. In the second approach, we need a comparator estimator. Now, here we want to use the tilting technique for regression function. Actually, we want to present the tilted linear smoother using infinite order as a comparator, which means that we are using the measurement distance approach. Here, as I mentioned earlier, we need a comparator estimator. We define it as our check. As you can see, this is an infinite order top flat kernel. With this definition for kernel, and this one is the Fourier transform. And also we have our hat, our proposed estimator, which we call it tilted nonparametric regression function estimator. As you can see here, this estimator has two types of unknown parameters. First is h, which is bandwidth, and then is a vector of pi's, which are the tilting parameters. So we need to estimate this theta. So we define theta hat as the solution to optimization problem. Here, it means that to estimate the theta hat, we minimize the distance between our hat, our proposed estimator, and our check, the infinite order top flat kernel estimator. There are three theorems that show how this proposed estimator enjoyed the same convergence rate as our check, our comparator. In additive setting, in case of being more than one predictor in the model, we want to fit the tilted additive model. So we use a backfitting procedures to fit this model to data. In this procedure, we have 5 steps. First, we take the intercept as a mean of yi's, and then we build the partial residuals. Then we fit the r hat j using the tilted linear smoother, and then we center these estimates, and then we repeat all the steps until we cannot see a big change from one cycle to the next. Now we want to show that how we can use this method in real data. As I mentioned in introduction, this type of models are really good for detecting nonlinear association. Here, I'm going to use this method in medical application to show how we can use this method to identify nonlinear association among the predictors and the outcome of interest. I'm going to use this method on diabetes data. So let's have a brief introduction about the data set, and then we have the model and interpretation. Diabetes mellitus is a metabolic disease defined according to an individual's level of hyperglycemia. The recent estimate shows there are 463 million people live with diabetes in the world. It is predicted that this figure will increase to 578 million in 2030 and 700 million in 2045. As the number of people with diabetes increase, the diabetes-related complication increase as well. We have two types of complications, diabetes-related complications. First are macrovascular complications, which increase the risk of a stroke, risk of heart attack, and also cause problems like poor circulation in body organs. And then we have macrovascular complications. This macrovascular complication can damage eye, kidney, or nerve. And also we have other complications that affect other part of body like teeth or gum. Here we want to talk about the macrovascular complications in the ocular surface. The ocular surface is an area that protects eye against the microbe trauma or anything. So this is the ocular surface. And the previous studies shows that diabetes can affect this area. So we analyzed a relatively large number of ocular surface images from diabetic patients to assess the association between demographic and clinical characteristics in relation to the area occupied by vessels in ocular surface. So here we have demographic and clinical characteristics of 168 diabetic patients. As you can see here, we have different types of predictors. We want to find the association between these predictors and our outcome, which is AOV, or area occupied by vessels in ocular surface in diabetic patients. We use the tilted additive model to find this association. Here you can see that first we fit the linear model, and then you can see the red line in each panel. You can see the green line in each panel that the linear models. And then we feed the tilted additive model, which is a nonlinear one, and you can see with the red line in each panel. And also, you can see that how nonlinear association and nonlinear feed could reduce the RSS, and we test this reduction, and it shows that for some of the predictors like BMI, age, or hemoglobin A1C, it suggests that the nonlinear one has a significant effect. I mean, the nonlinear feed has a significant reduction in RSS. So in final model, we can see that the effect of BMI, UPE, A1C, and BUN has a nonlinear effect on the AOV. And also, we have other variables that has a linear effect on the response. So our final model, which is a tilted additive model, is a semi-parametric model, a combination of linear and nonlinear model that you can see how it will fit to data. It's worth noting that the previous investigation on this data set using linear model couldn't find any significant effect. But now when we are using the tilted additive model here, we can find nonlinear association. So in conclusion, we know that the regression models are only available approximation to reality. These models are beneficial if they can capture some relevant and significant aspects of a reality. So we should use the regression, but not always the simple one. The regression should be enough complex to capture the relevant and significant aspects of reality. So non-parametric regression is a data-driven approach that can be used to examine data. So this is my main references, and this is the summary. We use this technique to improve actually we use the tilting technique to improve the performance of linear smoother, and also we extend the methodology in the additive setting, and we could find the nonlinear association in a real data set example. Thank you so much for attending this session.